Yeah, so my name is Alec. So this talk is about how to unify data preprocessing and training in machine learning pipelines using a new project we've created called Ray Datasets. So I'm Alex. I'm a software engineer at Anyscale and also a maintainer on the Ray project. And Clark, who I'm not sure if we figured out the technical difficulties yet, is also very similar to me. He's also a software engineer at Anyscale and also works on Ray. So yeah, let's get started. So just a brief overview of what we're going to talk about today. So the first thing we're going to talk about is essentially the state of how ML training and scoring pipelines in the real world look today and the types of challenges that they face. And hopefully that'll give you all some idea of the types of problems that we're aiming to solve. And then we'll go ahead and talk about Ray datasets, which is sort of our solution to these problems. And we'll see how it leverages Ray to provide a really clean, easy to use and performance solution. And then finally, Clark is going to finish us off by taking a look at a couple of use cases for Ray datasets and how some of our early production users are using datasets in production already. All right, so let's get started. So yeah, so if we take a look at how ML pipelines for just the preprocessing to training part tend to work today, is people tend to usually start by preprocessing their data using some sort of existing data processing framework. In a lot of cases, that's something like Spark or PySpark, or if you're really in the Python ecosystem, maybe you're using something like Dask. So now this is typically where you sort of hit the first bump in the road in terms of getting to, in terms of doing distributed training on your data later, is you have to find some way of like connecting your preprocessing to your training. And the typical approach that we've seen people use in production has been to take all of your preprocessed data and then write that to some kind of a distributed storage system like HDFS or S3. And then usually you'll have to like convert this data into like a Parquet format or something like that. And then you'll launch a completely new job, maybe it's even in a different language, and read all that data in from your storage, and then maybe perform some last second operations on it, and then finally train on that data. So as you can see, there's like, you need to stitch together multiple different systems that don't always work perfectly together in order to do this. And so typically this involves including another system, something like Kubeflow or Airflow, that's designed specifically for the purpose of like orchestrating your ML pipelines. So something like Kubeflow is really built specifically for machine learning, I think. And if you have something even more like a more complicated pipeline, you may need something like Airflow, like a general purpose workflow engine, to help you manage all of these dependencies and scheduling. All right. So now let's take a closer look at the challenges that the current systems in the wild face today. So there are a lot of performance overheads associated with how people are doing their building their ML pipelines today. If you're using something like Spark or something that's really based off of the Java ecosystem, a lot of users tend to find that they actually spend most of their CPU time in their job just serializing and deserializing their data, not doing the actual like useful compute work that they want to do. If you're using a system, if you're using other systems in the Python ecosystem because of the global interpreter lock, you typically need multiple processes, and you'll find that you spend a lot of your time again on overhead of just copying around the same data between different processes to actually parallelize your operations. And finally, there's this giant overhead here where we wrote all of our data to a storage system, and we didn't really need to do that, right? When we think about the pipeline, we think we want to do pre-processing and then feed the data into training. There's usually no hard requirement to actually be writing this data to storage, which is a very expensive operation since you're changing the format, you need to write it to a disk, et cetera. And then there's also a lot of like implementation and operational complexity, I think, with these pipelines. So you might have multiple languages. These different types of pre-processing versus training operations tend to be completely different workloads that require different types of scheduling and different types of optimization. And they use different types of resources. So pre-processing is typically done on large CPU clusters, whereas for training, especially in the deep learning world, we typically want to use GPUs. And then finally, there are a lot of operations that people in the machine learning and research communities really like and want to be able to use, but the current distributed systems out there for doing machine learning in production don't support. So one really big one here is per epoch shuffling. Anytime you're doing something with deep learning, it's really nice to be able to shuffle your data every epoch to increase your model's accuracy. But there's no really good way of doing that once you scale to multiple machines today. All right, so now we're going to talk a little bit about Ray datasets, and hopefully you'll see how Ray datasets solves a lot of these problems. So before we jump into it, we're going to take a quick look at Ray. So I don't want to focus too much on Ray in this talk, but I do think it's worth mentioning some of the really important properties of Ray that led us to build datasets on top of it. Because we can really leverage Ray to do a lot of the heavy lifting to solve some of those problems. So one of the most important things that Ray provides us here is a really efficient data layer. So Ray is largely implemented in C++, and so it's able to sort of bypass a lot of the issues that Python processes typically have by using shared memory to share memory between different processes on the same machine, which allows us to avoid doing a lot of copying. Because Ray also is really well integrated with Arrow, and so we're able to do things like zero copy reads that avoid having to deserialize your data once you read it into your process. You can just use that exact same representation that you already had stored in your object store. Ray also comes with locality-aware scheduling, so if you have a large amount of data, you don't want to transfer it around your cluster all the time, and so Ray will try to make intelligent scheduling decisions to do that. And then finally, if you do really need to move your data around the cluster, this is where you run into a lot of distributed systems challenges usually with overloading nodes and things like that. And Ray comes with built-in, the Ray's object transfer protocols are really built to handle these really, really stressful edge cases. And then the other really good benefit of Ray here is that it's really general purpose. So it has a resource-based scheduler that allows you to specify the type of resource that you want to give to different types of tasks within a single cluster. And so this allows you to do some things with CPUs and other things with GPUs very seamlessly and easily. It's also extremely robust and highly scalable. So it can run different types of workloads. You can even run an entire Spark cluster on top of your Ray cluster with very little overhead. And because it's very easy to build distributed systems in Ray, it really lets you access a wider ecosystem of other libraries on top of Ray too. All right, so now let's take a concrete look at what Ray Datasets is. So fundamentally, Ray Datasets provides essentially a distributed table abstraction. So this is very similar. This architecturally may seem very similar to frameworks you've already seen, like data frames like PySpark's data frame, for example. But we'll quickly go into what makes them different. But first, I want to talk about sort of what Ray datasets are designed to use. So the first and most important thing for Ray datasets is that it's meant to be an easy way for you to get your data from wherever you were doing a lot of your heavy lifting ETL type jobs into a Ray cluster, whether that data is coming directly from something like Spark or whether that data is coming from something like S3 already, like a storage system. We also want you to be able to do some amount of pre-processing on that data. There's always these types of last mile pre-processing operations that you may want to do right before you go into training mode that it doesn't make sense to do before in earlier stages of your pre-processing. And then finally, there are some types of operations that you want to perform on your data that require using a bunch of different resources. And these are things where Ray really shines. And so we want to enable you to do those types of operations using a higher level API using datasets. All right. So before we take a closer look, one thing I want to sort of emphasize here is that Ray Datasets is not meant to be a general purpose data frame library. So the place that we see datasets fitting into the ecosystem is we want it to work in, we want to make it sure it works well with the other data frame libraries. So datasets in Spark, for example, are not meant to be the same thing. What we sort of envision you doing is if you have a really large scale, ETL job for getting your data into a format to do machine learning on, we expect that you'll still continue to use Spark or Flink or whatever other systems you're using for ETL, and then use Ray datasets as sort of that last thing that lets you feed all of that like data analytics type of formatted data into like a format that's usable for training. All right. So to take a closer look at this, how we envision or how we see Ray being used as a data loader is you essentially start with your data in some other format outside of your Ray cluster. Maybe that's HDFS or S3. Maybe that's existing data frame already. And we want Ray Dataset to be sort of this like universal thing, like compatibility layer that you pass it into. And then we want to make sure that all of the ML training libraries you use are also compatible with datasets. And so you may find today that it's very hard, for example, to take something like Spark and pass the output of a large Spark job into something like TensorFlow. And so Ray Datasets is sort of supposed to make that possible and easy, right? So if you can convert all of your ETL data frames into a Ray dataset, you can do any last second operations you need and then feed that directly into your training framework. And the way we really accomplish this and are able to support so many things quickly is by really leveraging Arrow. So, this may have all sounded familiar to you because a lot of what we've talked about is what Arrow really solves on a single node. And so Datasets is meant to essentially play that role that Arrow plays on a single machine and sort of provide you that same benefit in a distributed setting. All right, so here we can take a quick look at sort of some of the formats that we already support for Ray Datasets. So as you can see, you can use whatever file formats you're typically comfortable with or read things in directly from other data frames. If this diagram is a little hard to read, I would encourage you to check out the Ray Datasets documentation, which contains these figures. And we'll have a link to that at the end of this talk. All right, cool. And so, it's not just important to support these types of operations, we want to make sure we can do them efficiently and easily. So the API that we want you to be able to use should be as simple as just read Parquet or read CSV, the exact type of thing you would be used to using in Arrow or Panda. And we also want to make sure that you can literally still convert to and from pandas. And, again, you should also be able to write things out to storage just as easily as you read them in. And again, so we really leverage Arrow here. And so that allows us to get really, really high performance on all of our nodes. And Ray lets us parallelize this easily. And so, even in production already, we've seen companies like Amazon that are using datasets for ingesting large amounts of data. And we've seen that, the sort of performance we see from Arrow on single threads, we're able to scale that up close to linearly to jobs that are in the petabyte or tens of petabyte range. All right, cool. So let's take a quick look at some of the last mile preprocessing operations that we support. So these are, in a lot of ways, some of the operations that you would expect out of most other libraries that you use for preprocessing. So you can do things like mapping, batching, filtering. You can do some aggregations on your data. And we also support some shuffle operations, which if you come from more of a systems background, you'll recognize these as sort of the notoriously hard operations that require a lot of communication. If you come from a machine learning background, these are sort of the operations that you just sort of expect to have and may be missing sometimes when you use other systems. So this is sort of just an example of what data may look like as it passes through your system. So if you start with some input, you may want to do some mapping on it. And then you might want to shuffle that data around between your different nodes so that all the data ends up in the right place before you reduce that data or do something like train on that data. And then finally, we'll aggregate that output together. Maybe that's the output of your model. All right. And so, there's also a bunch of other optimizations that we've built into datasets. So for example, we support pipelining. And so pipelining, if you're unfamiliar with the concept, is a way of making sure that when we have these really expensive clusters up, we're making the best use out of them. So if you imagine a typical pipeline, you may have a loading step where you load your data in. You might want to do some pre-processing, and then you might want to do some inference or score your data. And if we naively did that serially, we would find that we would start by loading our data, and then we'd pre-process, then we'd do inference. But before that inference step started, we just had a bunch of GPUs that we're probably already paying for that are sitting there idle doing nothing. And so the idea with pipelining is that it would be great if once we loaded our first bit of data, we're able to begin to do pre-processing on that immediately, and then begin to do inference on that immediately. So we begin to use our GPU a lot sooner. And while we're using the GPU, we want to also be loading other data and pre-processing other data in parallel. And Ray essentially lets you do this with a single line of code. Another really important concept that we support is windowing. And so windowing essentially is best described as, you can imagine what would happen if you tried to pass your entire data through a pipeline at once. You'll find that you need to be able to store, all of your data and a lot of your intermediate results in your cluster at a single time. So if this data is really, really large, you either need a massive, potentially infeasibly large cluster, or you might have to take a performance hit by spilling the disk. And so windowing is a concept where we can break our data set up into chunks that all fit in our cluster. And then pass each window in one at a time through our pipeline. And this will allow us to keep everything in memory, keep everything really efficient while not having to spill to disk. All right, cool. So now I'm going to pass it on to Clark, who's going to talk a little bit about the different use cases that people have with ML datasets and take a look at a couple of real world examples of how people are using it today.
Thanks, Alex. Awesome first half of the talk. My name is Clark. I'm on Alex's team, and I focus on a lot of data plane stuff, and I've been working on data sets a lot recently. So the two big use cases that we want to talk about that datasets really excels at is scalable shuffled ML ingest and efficient batch inference. Scalable shuffled ML ingest first, if you're not familiar, a little bit of background. What exactly do we mean by ML ingest? Fundamentally, this is just loading data into one or more model trainers, which on a single node can be pretty simple, but once you go into a distributed setting, things get a little bit more complex. But first, a quick little overview of what exactly is involved in ML ingest. Typically, you're going to be loading the data from storage. You are then going to want to partition the data into a shard per trainer if you're doing distributed training. You're going to want to batch the data into GPU batches. And then you're going to want to shuffle the data before each epoch. And this is typically done using local shuffling, where you only shuffle within a trainer shard before each epoch. That's the most popular option, primarily because global shuffling before each epoch is more difficult, but it actually ends up being much better in order to achieve optimal model accuracy within a set number of epochs. And actually, I'm going to do a quick little aside on that. First, for those that aren't familiar, why shuffle before an epoch? If we just shuffle globally once before training, why isn't that fine? The TLDR for this is that for certain models, per epoch shuffling gives you much better model accuracy after a set number of epochs within a given training window. And that's often a common constraint to users that we've talked to, where they have, for example, a 12-hour window where they want to train as many epochs as possible. So they care about high training throughput, and they want to get as much precision gain on each epoch. And fundamentally, if you want to know why this is the case, shuffling before each epoch, it decorrelates samples within and across batches. And in this case, yeah, for doing this before each epoch, it reduces variance, it improves the generalization of the model, and it prevents that pesky overfitting that we all super hate when training our models. I would go in a little more detail, but I think I'm a little short on time. But fundamentally, there are a few papers out there that have examined this. I definitely would recommend one, a convergence analysis of stochastic gradient descent under shuffling. Super great paper. But generally results in an improved statistical gain for each step in the training process if you shuffle before each epoch. So first, why exactly is this even a problem? Aren't you just loading data into your trainers? Why isn't this just simple ingest? Why is this tough? Well, first, at a certain data and cluster scale, you need parallelized scalable reading from storage. If you did it all serially with a single thread, your trainers would be super unhappy because they'd be waiting forever. And then you also need to try to not waste your idle. You don't want your GPUs to be idle while you're reading and shuffling data. As Alex talked about, just because your GPU is idle doesn't mean that you're not paying for it. You're almost always paying for that GPU that's just sitting there. So for example, here, this is a situation where a trainer is waiting for data to be loaded and shuffled before training on each epoch. And as you can see, we have all of these gaps where the GPU is sitting idle. So that's all time those are all times when you're paying for a GPU, but it's not actually being used. And then also a few other things that make this hard. Well, first, we have to keep the API simple, despite the fact that we're now talking about large scale data, and we're also talking about large clusters and distributed training. We still want the API to be as simple as possible. Also, the full pipeline may not fit in memory, as Alex just talked about when talking about windowing. Your entire working set for your ingestion pipeline, especially when you're doing shuffling, which will create intermediate copies of your data set, might not all fit in your cluster's memory. Local shuffles, they hurt model accuracy, as we talked about before, compared to a fully global shuffle. But global per epoch shuffling in a distributed setting is fundamentally pretty difficult because of this like all-to-all communication. Basically, there's between the mappers and reducers in a shuffle, there is a ton of data interchange, and this can result in a lot of transferring of data over the network, which is not fun. So how does Dataset solve this? Well, first, as Alex hinted at, our IO layer is super scalable, very easy to parallelize reading from like high bandwidth storage solutions like S3 and HDFS. For example, that's all you have to do right there to launch 20 parallel reading tasks from S3. It's very simple API, but a very powerful IO layer under the hood. And just to give you an idea of what this would look like, 3 parallel read tasks from S3. You can feed your data to the trainers pretty quickly. Also, like, how exactly do we keep the GPU from sitting idle? How do we keep the GPU saturated? With datasets, we use the pipelining of the preprocessing and shuffling stages with training. And instead of having these like little gaps of GPU idle time, you will instead see that by pipelining the shuffle data loading stage with the model training stage, we are able to limit that GPU idle time just to pretty much the first epoch. After that first epoch, since we're concurrently loading and shuffling the data for the next epoch while training on the current epoch, you'll see that the trainers never really have to wait for the data loading and shuffling to finish. And as long as your shuffle data loading throughput is more than your training throughput, then basically after the first epoch, the trainer should only see hot shuffle data. And then per epoch shuffling, it's a difficult distributed problem. How do we do it efficiently? Well, as Alex talked about, our great distributed in-memory object store allows us to do super efficient transfers and also zero copy reads for workers that are on the same node. It allows us to do these shuffle operations, the map and reduce stages very quickly. We also have locality replacement of shuffle shards onto trainers. And that's as simple in this API example, where we give these locality hints, where we say like, hey, these are all of the trainers. Do your best when splitting the data set into shards for one shard for each trainer. Do your best to co-locate those on the same node so you don't have to transfer data over the network. So it's just small optimizations like that that can make a huge difference in like your actual shuffle data loading throughput, which of course affects your training throughput. And so here's an example there of what this little workflow translates to in terms of the pipelining, the repeat of the random shuffle on each epoch, and the eventual split of the shards to the training workers. And then as Alex also talked about, we use windowing in order to limit the working set size for a shuffled ingestion pipeline. And this prevents us from running out of cluster memory and prevents us from spilling to disk. So as you can see here, we're only doing our shuffle data loading on one window at a time. So despite us dividing the data set into 3 windows here and limiting the size of that intermediate data set that's in the cluster just at one time, this is all still just one epoch. Here you are trading off shuffle quality with cluster size. By windowing, you can have a smaller cluster since the working set size is smaller, but you're going to no longer be shuffling on the entire global data set at once. You're only shuffling on smaller windows, so your shuffle quality takes a little bit of a hit. And we also keep the API very simple. I'm gonna go through this a little bit quickly since we're limited on time. The trainer API here is just like a simple task that consumes a shard and then trains on GPU batches. And this is what you would probably have right here, this code example for a ingestion pipeline on small data and when training on a single node. So relatively simple. You basically read Parquet, you repeat for the number of epochs that you want. You should make sure that each window is shuffled, and then you feed that data set to the trainer for it to consume and train on. To extend this to a large data scale and a multi-node distributed training setting, this is really all that's required right here. You window to constrain the working set size, and you split the data into shards and feed those to trainers. So case studies. First, a little bit of background. Common problem here is like the existing solution is a bottleneck in their training pipeline. So this is where shuffle data loading is really the issue, why they're not training as fast as they want. And then also the models are shuffle sensitive, where the shuffle quality does in fact affect model accuracy. We have two case studies here, a high-tech ML platform that's a startup that's currently in stealth mode. Their old solution was actually writing data to S3 and then using Petastorm to load it into Horovod. For those that don't know, Petastorm is an ML ingest library from Uber. Our solution that we pitched was porting the pandas to S3 portion of the pipeline to Dask on Ray preprocessing, and then feeding that directly to Ray Datasets for ingestion into the Horovod trainers. And then the other case study was a large tech company in transport space that was originally loading data from S3, again, using Petastorm. And we actually said, continue loading data from S3, but this time use datasets. Both case studies suffered from the above common problems, by the way, like both of these had the same issues. So for benchmark results, very quick summary, Dask on Ray and datasets was 8 times faster than the old solution on a popular New York City taxi dataset. And also for the other case study where we're still loading from S3, we were 4 times faster. And this is, by the way, when we're doing more work, because we're doing a global shuffle instead of a local shuffle. So you're getting a higher quality shuffle and better performance, even at small scales. And then we're also working on more comprehensive benchmarks that are in progress. The other use case I'll go over very quickly is batch inference, where you do some pre-processing and then you perform model inference over batches of data and save the results. So there are a few issues here. There are some scheduling issues. You don't want to transfer the data around the cluster, and you want to reserve GPUs for a fraction of the time, and you need to keep the GPU saturated, as we talked about before. We solved the scheduling issue with Ray's great scheduling properties, automatic data locality, and Ray's resource scheduling. And we use pipelining to solve the issue of idle GPUs. And the case studies, we have a startup that's processing drone imagery and a high-tech ML platform that's got an existing solution just using pandas to torch. And the results, just to skip through it, we were 5 times faster on this data set for batch inference, as you can see from these graphs here. And so we provide more resource efficiency and better performance even at small data scales. So in summary, existing ML platforms or ML pipelines suffer from a lot of issues, and Ray datasets, we hit that mark using hyperscale implementations of ML operations like Shuffle. We keep the API simple, and for ML ingest and batch inference, we beat the existing competition by a lot in terms of performance. So yeah, I had to go through the end there pretty quickly, but yeah. Thank you for listening to the talk. And then we're probably a little bit out of time for questions, but please hit us up on our discussion forum. Check us out online, and we're hiring. So if these problems are interesting to you, please come check us out.